The picture in the background was painted by one of my former students, Shan Ding, who is now an associate professor and doing quite well. Uh, to start, you mentioned that I did Cook's Distance. I thought I'd start on a light note and tell you my favorite story about Cook's Distance. I was attending a workshop at the Newton Institute for Mathematical Sciences in Cambridge, England. And between sessions, I happened to be chatting with Mike Titterington. And one of Mike's students walked up, and of course, Mike introduced us. And he mentioned that in his introduction of me, he mentioned that I was the author of Cook's Distance. Well, the student looked at me and his eyes got kind of big and his mouth dropped. And he said, "I thought you were dead." So that's what happens when you have things named after you. Some people think that you don't get things named after you while you're living, only when you're dead. Anyway, today I'm going to talk about partial least squares. Partial least squares has been around for a long time in the applied sciences, and particularly in chemometrics, although it's not been very visible in statistics. And from time to time, I wonder why that was, why there is a regression method that's used extensively throughout the applied sciences, but has very little visibility in statistics. And I can't think of an institution where partial least squares was a required part of the core curriculum. That was the case until about 2013, and then things started to change. And over the past decade, there's been a lot of development in partial least squares, connecting the ideas with more standard ideas in statistics. And that ended up in a book. After about a decade, Liliana Ferzani and I decided that there was enough material to put together a book describing particularly the results of the past 10 years. And so that's what we did, and it was published in 2004. And what I'm going to tell you about today is highlights from what we learned in the past decade. Now, these highlights, there are a lot of interesting things going on with partial least squares. And it was kind of hard to choose which ones to pick. But nevertheless, I tried to pick the ones that I thought were the most important. So starting with a little background, partial least squares is attributed to the work of Hermann Wald, who lived between 1908 and 1992. He was a PhD student of Harold Cremier, and he has lots of interesting contributions in statistics. He's probably best known for the Cremier-Wald theorem, but he also did things in time series causal modeling. And for our purposes today, he inspired and laid the foundations for PLS and PLS regression. So the whole theory, the whole idea goes back to Wald, particularly to his work in the 60s and 70s. And every time I think about this, think about what he managed to accomplish during that time period, it's incredibly impressive. Whoops, sorry. There we go. So PLS is a regression algorithm. There isn't a model that it's trying to fit, or there wasn't for decades. There's not a well-defined parameter that it's trying to estimate. It's simply an algorithm that produces estimates and predictions, primarily for linear regression. It was introduced in around 1980 by the Scandinavian chemometrics community. And when I think of that community, I think mainly of Hermann Wald, of course, and Svante Wald, his son, Harold Martens, Tormod Nays, and Inge Helen. There are lots of people from the Scandinavian chemometrics community that contribute to this methodology, but those happen to be the 5 people that I think of when I think of PLS. It has had a small footprint in statistics. There are a few papers that are interesting. Helen gets cited frequently. Frank and Friedman, in their 93 technometrics paper, is cited frequently, but there's not much in way of statistical literature that the statistics profession found to be, I think, compelling. Some people attribute that to different cultures. There's Leo Breiman's 2 cultures, and that could account for part of it. Helland in 2018 described the difference as creativity, which is what takes place in chemometrics, versus rigor, which what he said takes place in statistics. The situation was like this and kind of static, little things appearing here and there in statistics, a lot of things appearing in chemometrics, a lot of things going on in the applied sciences. And that was until I published a paper with Inga Helland and Jiwa Su on the first links between partial least squares and envelopes. And what this paper did in 2013 is it laid the foundations for a beginning of a new chapter in partial least squares, linear regression. And that's what I'm going to tell you about first today, is how that paper and subsequent papers developed partial least squares. So the context for today is going to be a standard linear regression context. We have independent observations on y and x, which has a joint density. Y is real, x is in RP, a little notation there that's pretty standard. And the goal, of course, since this is regression, is to understand the conditional distribution of y given x and to do prediction. So what are the key findings? Now, what I'm doing in this talk is a little bit different than a standard talk. I'm going to give the findings first. I'm going to tell what I think is important about partial least squares regression, and then later I'm going to explore these findings and kind of develop them a little bit. But the findings or the conclusions are going to come first. So, number one, the heart of the partial least squares regression algorithms are methods for reducing the dimension of the predictor vector in the conditional mean. So imagine you have a regression problem. What you want to do is get a handle on the conditional mean. You may assume it's linear or not, but that mean depends on a lot of predictors. And what you want to do as part of your analysis is reduce the dimension of the predictor vector. That's what partial least squares does. It compresses X into W transpose X, where W is a P by Q matrix with rank Q, which is less than or equal to the minimum of N and P, and hopefully it's a lot less. Q is called the number of components in partial least squares. So if you start off with 100 predictors and you imagine reducing it to 10, that's quite a substantial reduction. Now, the key population property is partial least squares produces a W, so that the conditional mean of y given x is exactly the same for all values of x as the conditional mean of y given W transpose x. And that's the notion of dimension reduction. That's what partial least squares tries to do. Now, the conditional mean may be known in functional form. You may say it's exponential, or you might say, for example, it's just linear mean. So you're doing linear regression, or it could be unknown. In any of these cases, the algorithm that partial least squares produces gives you a nice dimension reduction. So imagine, for example, that your conditional mean is unknown. You have 100 predictors, and you manage to reduce it to 2 linear combinations. So Q is 2 by using partial least squares. You don't know what the conditional mean is, but now you're in the position of being able to do graphics that will give you lots of information about the conditional mean. So the dimension reduction might be a prelude to doing graphics. Or it might be a prelude to prediction, estimation, a lot of different things at this point. The algorithms themselves are difficult to understand. If you look at these algorithms, unless you're a lot better at computing and thinking about what they're doing than I am, they're really difficult to understand. My first exposure to partial least squares was when I was working at Los Alamos National Laboratories in the early 80s. And a fellow that I was working with came in and said that the chemometricians were really excited about a new way of doing regression, and would I take a look at it and tell the group, the statistics group, if there's anything there. And I said, well, of course, I'd be happy to. What he gave me was several pages of Fortran output. And I came to realize that what he was asking me to do is to reverse engineer that code, figure out what the code was computing, and then find out if that was a reasonable thing to do. I looked at the code for a couple of hours, and I decided that reverse engineering someone else's code was not something that I was very good at. And so I took the code back to him and I said, well, I would rather not do this. Let's work on something else. He agreed readily, and that was the last time I thought about it for a while, and that was my exposure to partial least squares. One of the things that I came to understand later is the code was developed, it was adapted. The code was adapted from stuff that Wold had done in the 60s and 70s. Computing in the 60s and 70s was a lot different than it is today. There weren't nice routines available, for example, for computing spectral decompositions. Now, the partial least squares algorithms depended on spectral decompositions. So what the authors of the algorithms did is they put in routines for doing those decompositions. They didn't tell you what they were doing, they just put them there. So you had to figure out all of this stuff going on. And I'm glad that I decided not to do that. So nevertheless, what we were able to prove, thinking about the algorithms, is that point 4, partial least squares dimension reduction, the algorithm, which was developed around 1980, at least the first one, is an envelope method. Envelopes were developed around 2000, were developed first paper in 2010, and envelopes are special cases of sufficient dimension reduction. So now, with that series of containments, there are a lot of things we can say about partial least squares dimension reduction algorithm because it inherits properties from sufficient dimension reduction and from envelopes. And it's that direct connection that starts to open the door to understanding what partial least squares regression is doing. Once we have an estimate of W is the thing that partial least squares is producing. Once we have an estimate or estimator of W, we simply do regression fitting of Y on the reduced predictors W hat transpose X. Collinearity, PLS is relatively immune to collinearity, a property that's inherited directly from envelopes. Now, to performance. How does PLS regression perform? Well, it does a pretty good job. The first paragraph there under point 6 says, the predictive performance of partial least squares can be much better than ordinary least squares, even if n is a lot bigger than p. So even if n is a lot bigger than p, there are still good reasons to think of partial least squares. I mention this because it's kind of a scuttlebutt that partial least squares can be used when n is small relative to p or not so big, but in my experience, it should be considered as an alternative to OLS in virtually every problem. Now, regardless of the relationship between n and p, one of the strengths of partial least squares is that its estimators can converge at the root n rate, provided that the signal is sufficiently strong. You can have p bigger than n. You can have p 1,000 and n 100. The convergence rate is still root n. It doesn't care what p is, provided the signal is sufficiently strong. A sufficiently strong signal, in this, you can think of it as meaning simply that a lot of the predictors matter. It's like anti-sparse methodology. You don't want to assume sparsity where just a few predictors matter. What you're assuming, or what you're relying on, is that many predictors matter. And that's where partial least squares really does a very good job. So you can think of it as being most useful in abundant regressions. Now, its estimators can be inconsistent in regressions with weak signals. That is, when you're invoking sparsity. If you invoke sparsity to handle a high-dimensional problem, you don't want to use the ordinary partial least squares. There are versions of partial least squares available for sparse regressions, but the ordinary version, the one that I'm talking about today, should not be used if you're going to invoke sparsity. Now, in chemometrics, sparsity is the exception rather than the rule. Their regressions are nearly all abundant, and it works really well. That's why partial least squares works really well for them. One of the things I like about this sort of dichotomy that I'm talking about is that partial least squares regression provides a serviceable alternative to sparse methods in high dimensions. Over the past couple of decades, statistics has really climbed on the bandwagon of sparsity. It's not unusual at all to see papers that start off with, if it's sparsity, if it's high dimensional, then naturally it must be sparse. Okay, if it's high dimensional, then naturally it must be sparse. I don't find any sense in which high dimensional regressions are naturally sparse. None at all. Sparsity is a reasonable model, but you have to have assurances other than just the fact that you're in high dimensions. So this gives an alternative to assuming sparsity. You don't have to assume sparsity. You can rely on abundance or something between abundance and sparsity, and their PLS should work really well.
Sorry, can I ask a question, clarifying question?
Sure.
So going to this comment about sort of the root n convergence of the estimates, can you please sort of elaborate on sort of what the estimates mean here in this case? That
Okay, yeah, fair question. In this case, I'm referring to linear regression. And in linear regression, the estimates are of the conditional mean, the expectation of y given x, which is just a linear function of x, or of beta, the regression coefficients. So for either of those things, it will converge at the root n rate if the signal is sufficiently strong. I expect that there are going to be similar results if you have a nonlinear regression setup, but that has not been studied to my knowledge because there are additional intricacies that you'll get into in nonlinear regression. But for linear regression, that's where that paragraph is operational. We'll see that more later on in the talk, assuming that time permits.
I also have a question, if you don't mind, now that we're stuffed. You actually had, you described, and maybe you'll get to this in just a few slides, but you've described partial least squares at the population level as saying the mean of y given x is equal to mean of y given w transpose x. Right? So is that an assumption that you're making? Or
no,
so,
that's a theorem.
So and is this saying that, well, so I guess if you don't fix the dimension of that matrix, if you don't fix the Q, I think Q is the reduction,
the dimension of the matrix, right?
I guess if you allow W to be the identity, you always get back to, so you're saying there is at least one, the identity will work, but we're interested in finding the smallest, the W that leads to the smallest number of linear combinations. And at worst, we're back to the original case where we're not doing any reduction. But so there may be multiple, there are potentially multiple W's. And so which then are you going for? Or does it not matter because you're going for the regression function?
Fair question. It doesn't really matter because the whole thing centers on the span of W, and we'll get to that as we go along. It's only the subspace span by W that matters. You can reach into that subspace, pick any basis you want, and use that and for your W.
Because it leads to the same regression function at the end of the day anyways, even if you have multiple W's, right?
That's right.
Thank you. That's your
So if you think about the expectation of y given x, if I multiply x by a non-singular matrix, that doesn't change at all. It's exactly the same. Mm-hmm. So that's why it's only the span of W that matters.
Thank you. Thanks.
But just to clarify, to reiterate the question of Marco, are you in the search for the smallest basis that spans that space? The dimension Q, is that the smallest possible that you are looking for, that you're after? Or do you care
we're getting
about...
a little bit ahead of ourselves here, so let me define it for you.
All right. Okay.
To take any W and stick it in there, then take another one and put in there, and then take the intersection of the spans of all those W's. That's the one we're after. Okay. So it's indeed the smallest one because it's contained in every W that works.
Okay. Thanks.
Yep. So some uses for partial least squares, just for the fun of it. I went to Google Scholar when I was preparing this talk, and I asked it how many references there were since 2021, and there were 18,500 Google references in the last 4 years. That's a lot. And I looked through some of the papers that it referred me to, and they're doing partial least squares for evaluation of groundwater quality. You can kind of read the list. Groundwater quality, predicting water quality, classifying chicken egg fertility, and a new modeling method for fault prediction of, I have to slow down, for wind turbine gearboxes. It's all over the place. And that's the only point of this. So then the promise, what's the promise? Here's a little example. This is to predict the protein content of Y, protein content Y of beef based on spectral measurements at 50 wavelengths, 103 observations. And the picture was generated by using 5-fold cross-validation for the root mean squared error. Blue is PLS, black is ordinary least squares, and this whole thing is linear regression. You can see that partial least squares does really well in terms of the prediction error, which is on the vertical axis. If you have the horizontal axis here is the number of components. So if I have 1 or 2 components, I'm going to kind of blow it. You have to be careful with partial least squares not to get the number of components too small. But if I have 3, 4, 5, 10, even up to 15, I'm going to do really well compared to ordinary least squares, even though with 50 observations, with 103 observations and 50 samples, I can certainly compute the ordinary least squares estimator. So that's the promise of ordinary least squares, of partial least squares. So what comes next? Now we're going to go to some of the questions I think that people have in the back of their mind. Understanding partial least squares via envelopes, and then we'll start with a model-free treatment, and then we will eventually specialize to linear models. So the overarching idea, the way I'm presenting this now, this didn't come about until a couple of years, until 2021, so 4 years ago. So this is relatively new stuff, and it's not normally associated with partial least squares. But the foundation of partial least squares we can think of as coming from sufficient dimension reduction. So what we wish to do is to compress X into W transpose X without loss of information on the conditional mean. Formally, what we're going to do is we're going to say, I require Y to be independent of the conditional mean, given the projection of X onto the subspace spanned by the columns of W. So that's the basic idea. The span of W is called the dimension reduction subspace for the conditional mean. And this idea was explored way back in 2002 by myself and Bing Lee in an annals paper. We want the smallest W so that this happens, and we define the smallest W to be the intersection of the spans of all W's that satisfy that particular equation. So we take the intersection of all of them, that's what we want, and that's called the central mean subspace. There are a few equivalent statements written there. The first statement is the same as the statement at the top of the page. Y is independent of the conditional mean given the projection. The next one is just to say that the covariance between Y and the conditional mean given W transpose X is 0. And the third one is simply to say the obvious, that the expectation of Y given X is now a function of W transpose X. There are lots and lots and lots of methods that for sufficient dimension reduction. There are lots of methods, but not quite so many for the central mean subspace. But they all suffer, or probably nearly all suffer, from the usual regression plague of collinearity. If you have collinearity in X, the methods that are available in the literature for estimating the central mean subspace, for estimating the central subspace, for doing sufficient dimension reduction, don't perform so well. In the early years of sufficient dimension reduction, the simulations that were published nearly always had the covariance matrix of X equal to the identity, because that minimizes the collinearity. So what do we do about collinearity? That's where partial least squares and envelopes come in. So to handle collinearity, we add a condition. So envelopes and partial least squares add the condition that the covariance between QW, the projection on the orthogonal complement of the span of W, QW times X and PW times X, that covariance is 0. So we're saying we want linear combinations of X that we can see crisply. We don't want them to get confused with other linear combinations because of collinearity in the data. So we add the condition that the covariance between these two things is 0, and that brings us to a relatively new idea where we have two conditions. Condition A is for the central mean subspace. Condition B handles collinearity. Now what we do is we take the intersection over all W's, span W's, that satisfy A and B, and what that turns out to be is the smallest reducing subspace of sigma X that contains, that is, envelops the central mean subspace. We denote this as E standing for envelope, sigma X being how we're controlling the correlation, and this being what we're enveloping. So we read this as the sigma X envelope of the central mean subspace. Now there's a little cost here that I haven't found to be very high, and the cost is that the direct methods for estimating the central mean subspace are estimating something that's smaller than the envelope, since the central mean subspace will be contained in the envelope of that subspace. That is, almost by definition, it'll be contained in the smallest reducing subspace of sigma X that contains the central mean subspace. Now, the name envelope came about because when I was developing envelopes with Bing Lee and Francesca Charmonte, we were kicking ideas around and talking about it one day in the conference room at Penn State, and we started using the word envelop, one thing enveloping another. We started calling it an envelope, and that just stuck. So it wasn't really a conscious choice. It just kind of evolved from our informal conversations. Now, what does all of this have to do with PLS? Under mild conditions, the span of W for PLS is exactly the smallest reducing subspace of X that contains the central mean subspace. That's what PLS is after. It's after a basis. Its algorithm produces an estimate of a basis for the sigma X envelope of the central mean subspace. Q is now interpreted as the dimension of that subspace. So that's the link. PLS is basically an envelope method. That is, it's estimating an envelope basis from its algorithm. Now, how in the world Wold could have thought about that when back in the 60s and 70s, I find it utterly amazing. But that's what it is, and that's been proven. That's a theorem. It takes several pages to prove. It's not an easy thing because you have to deal with the complications coming from the algorithm. So we have envelopes in PLS are descendants of sufficient dimension reduction. Sufficient dimension reduction is at the top. That gives rise to envelopes, which is a descendant of that. Partial least squares regression is a descendant of envelopes. Partial least squares linear regression is then a descendant of partial least squares regression. So I hope that kind of answers the questions that were raised earlier, or at least sheds more light on the answers. So what are we going to do now? Well, now we're going to say, let's look at the envelope / PLS version of the linear model. Let's do things that are a little bit more concrete, and let's think about the linear model. So now we let the columns of the P by Q matrix W form a semi-orthogonal basis for the sigma X envelope of the central mean subspace. The central mean subspace in this model is trivial. It's just the span of beta. So we're now asking for the sigma x envelope of the span of beta. That is, we want the smallest reducing subspace of sigma x that contains the span of beta. Now, once we've defined this, we can reparameterize the model in terms of that W. And that happens in two ways. The first way is just a reparameterization of the mean. That ensures that y is independent of the conditional mean given W transpose x. If I know W transpose x, there's no more x in that model at all. So clearly y is independent of the conditional mean given W transpose x. The second part decomposes.
Sorry, can I ask you something? Sorry, I apologize, but why is linearity preserved? If you condition on Wx, why is the mean of x given Wx still linear?
Well, because this model depends on x only through W transpose x.
I see.
If I condition on W transpose x, there's no way for the model to impact that.
Well, but I understand that, but why couldn't it be that the mean of y was a nonlinear function of W transpose x? Why is linearity preserved on the W transpose x scale? You know, when
we start with this model. This is our
Right.
this is the starting point.
right. And if I take the expected value of y given W transpose x, I get alpha plus beta transpose the expected value of x given W transpose x plus the mean of epsilon. So
Right.
why is the expected value of x given W transpose x still linear on W transpose x?
Because we aren't modifying this model in terms of x at all. We're modifying it in terms of beta. What is beta? Beta sits in this subspace.
I see.
This subspace has basis W. Therefore,
see.
I can express beta as W times a vector of coordinates eta. So W
I got
times,
it. I got it now. Thank you.
okay?
Thank you.
So this first statement ensures that we get this. The second statement ensures that the covariance between these two things is zero. Now, it's the second statement that makes this absolutely unique, because we're not only dealing with the conditional mean, because we're dealing with collinearity, we also impact the marginal variance of x. It has to have this decomposition to ensure that this covariance is zero. And that's one of the unique things about the envelope PLS approach, is that it deals with covariance and it impacts the marginal covariance matrix of x. An implication of that is that PLS gains information from the marginal distribution of x, so it is not an ancillary statistic. Conditioning on x, which is a standard thing to do in regression, loses information that PLS uses and the envelopes use. So we have to have a joint distribution. We make use of the marginal of x. It's not an ancillary statistic. Conditioning on x loses information. So what about estimation? Now, what do I mean by estimation? Estimation starting from that model. Well, I could assume that x and y are multivariate normal and then just do the required algebra and get the likelihood. Now, the likelihood is not convex. It will be a function of the span of W. It will not be a function of W per se, but only of the span of W, because it's this subspace that's the parameter. It's not convex. It requires n to be a lot bigger than p to work well. And the optimization is now over a Grassmannian. It took us a couple of years to get to the point where we could do this kind of optimization reliably, because optimization over Grassmann manifolds tend to be really bumpy, and you had to work very hard to avoid getting stuck in a local max. On the other hand, PLSW from its algorithm, which allows n to be less than p, is easy. You just run the algorithm and you get your W. Now, either way, whether you get W from the envelope method or W from PLS, in either case, beta hat is this weighted function, weighted least squares function of W and the marginals of the sample covariance matrix of X and the sample covariance between X and Y. So that's beta hat. It doesn't matter where W comes from, that is envelope or PLS. You do exactly the same thing once you get W, because the envelope and PLS are trying to do exactly the same thing. They're both trying to estimate that span. So let's go back to the beef protein example, slow things down a little bit. The blue and the ordinary least squares line are the same as before. The red line, which is now new, is the envelope line. Envelopes actually do better than PLS at the lower number of components. You don't have this striking penalty that you might pay if the number of components is too small. But otherwise, they do pretty much the same thing. So the envelope methodology, and this is the envelope methodology for the linear regression model, assuming that X and Y are multivariate normal. Oops. Now, another data set. This data set is muscles. It's a nice small data set. It's something that you might use in a first course in regression, and that's why I'm using it here. To kind of make the point or reinforce the point that partial least squares can be used in lots of different contexts. So the data is from an ecological study of horse mussels sampled from the Marlborough Sounds off the coast of New Zealand. Y is the logarithm of the mussel's muscle mass. And there are only 4 predictors: the logarithms of shell height, shell width, shell length, and shell mass. 79 observations, and there's strong inference for one component. There is a plot of Y versus the PLS fitted values. Plot is used as a diagnostic, just like you'd use a plot of Y versus OLS fitted values. And I don't see anything unusual there. It looks like a pretty good fit. Here is a plot of the OLS fitted values versus the PLS fitted values, virtually on a straight line. Now, the first reaction I had when I looked at that plot is, well, you don't need to use PLS in this model at all. You just go ahead and use OLS. But that was kind of a premature reaction, because PLS actually gives you a lot more information than OLS if you look at the coefficients and their standard errors. The first block, OLS, are the coefficients and standard errors, usual standard errors. Second block, PLS, estimates and standard errors. Third block, envelope, estimates and standard errors. If you stay within the OLS block and you were thinking of students in a first course in regression, what would the students do? What would they have been taught to do? Probably. And you'd look down there and you'd say, well, there's only one predictor, and that's the one corresponding to beta 3, that looks like it's significant given the others. So maybe what I'm going to try and do is start deleting predictors one at a time and do a backward elimination. That's one thing that's taught in classes. There are other things that could be taught, but the impression that you get is that there's only one clearly important predictor. On the other hand, when you do PLS, you get a really different impression. Look at those standard errors. They're tiny compared to the estimates. Same thing with envelopes. The envelope standard errors are a bit less than the PLS standard errors because the envelope is doing maximum likelihood and PLS is basically doing a method of moments. But nevertheless, they're both much better than ordinary least squares. And as we saw before, the fits are virtually identical. And you can kind of see what's happening when the standard error of the estimate is large from OLS. that gives partial least squares and envelopes room to move around. The estimate is here and they're at standard error. So the estimates change when the standard errors here in OLS tend to be not small relative to their estimates. So this is a good reason for thinking about doing partial least squares in kind of run-of-the-mill problems. Here we have 4 predictors and what, 79 observations.
I have a question on this slide, if you don't mind.
Sure.
So what's so in OLS, okay, so the betas are the ones corresponding to each covariate, but now partial least squares, you're taking linear combinations to form new variables. So
Yes.
what are those betas now corresponding to?
To get those betas, you take W hat and you multiply it by eta, which you've estimated.
I see. So the eta is the coefficient vector that is in front of the transform variables, and then you just basically move back. So you're still going after the same thing, basically.
Yes, you're still going after exactly the same thing.
Great, thank you.
And sorry, related question, because you mentioned that sort of PLS obviously could also be used in settings where P is larger than N. So in that case, if the W matrix is not full rank,
The W matrix will be
identifiability?
It's guaranteed to be full rank because the W matrix estimates a basis for a subspace, and you can always pick the basis to be full rank. In fact, it won't be a basis if it's not full rank.
I see.
And one more question. When you do the standard errors for the PLS and the envelope, are you incorporating the uncertainty in the estimation of W as well as eta?
Yes,
Both.
but we are not incorporating the uncertainty due to Q.
All right.
So-
So that's your, okay. So it's kind of, isn't it cheating a little bit because you are pretending that you knew Q beforehand?
Is it cheating a little bit? Yeah, it's definitely cheating a lot more than a little bit. But there's other literature that I haven't talked about here and that I don't plan to, that incorporates the uncertainty due to Q. And most of the time, the uncertainty due to Q is small if you have really strong inference for Q. Now, you can estimate Q by cross-validation. You can estimate Q if you're going to do maximum likelihood, you BIC or AIC, and you can do model averaging to get Q. All of those things tend to give you exactly the same bit of information if the inference on Q is strong. If the inference on Q is weak, then you're going to pay a substantial price. That's why I said on the previous slide, or in one of the other slides, strong inference for one component Q.
Okay, thank you.
So I'm definitely leaving out a bit here of the theory, and that's how you deal with Q. But there just isn't time. And I say I'm running out of time now. There just isn't time to do that level of detail.
Excuse me. I also have a question about these two sets of results between OLS and PLS. Given that their fit are pretty much the same, how do I think about the fact that one identifies only one significant variables, whereas the others are all 4 being significant? Like, yeah, how do I know which one should I trust?
You'll trust the one that Q is equal to 1 because that's the additional information you're bringing to the problem. So because in this example, I have not taken into account the uncertainty in Q, what this amounts to is additional information. So I'm giving the model the additional information that Q is 1. And that's what accounts for the massive reduction in standard errors.
And does the case,
It's like any tuning parameter for any model. If you know the tuning parameter, or you pretend you know the tuning parameter, whether you're doing lasso or whatever, if you have a tuning parameter doing sparse fits, it's the same kind of problem. But here we have gone further, although I don't have time and I didn't even plan to do it in this talk.
And in this case, Q equals 1, does that correspond to what others have called single index models? Is that the same?
Yes, that corresponds to a single index model. Yes, you're exactly right. This slide just says a comparison of PLS and envelopes. There was a big simulation and data analysis study done in the journal Chemometrics and Intelligent Laboratory Systems by Remmel and his co-authors. And their conclusion was really quite strong. Their conclusion was, and it's in italics there, that's a quote out of the paper, analysis using both simulated data and real data has shown that the envelope methods are more stable, less influenced by predictor collinearity, and in general perform better than PCR, principal component regression, or partial least squares methods. These methods are also found to be less dependent on the number of components. And we saw a little example about why about them being less dependent on the number of components. Now, there's a curious thing that happened here. When they did their study, they had lots of problems where n was a lot less than p. And so how in the world could they use envelopes when envelopes, the envelope methodology is maximum likelihood and it's got to be a lot bigger than p? Well, they reduced the number of predictors by principal component analysis prior to applying likelihood-based envelope methodology. There is no theory for that I know of. And so that's an open question, but judging from their simulation, it's something that's in the future needs to be studied because it evidently worked really, really well. Asymptotic performance of PLS in linear regression. We talked about this at the beginning. I gave you kind of an overview. Here is just a little bit more detail. When we were doing our asymptotic analysis, and this is just for linear regression, the signal turned out to be the trace of the variance of the reduced predictors. And for the purposes of these calculations, we're going to model that with p to the t power. So we can think of p to the t as the number of active predictors, or asymptotically equivalent to the number of active predictors. So the table gives the orders of this difference, the estimate of the conditional mean, and how well we're doing to estimate beta. And it gives those orders as n and p are going to infinity. So here we have the value of t. If t is equal to 1, then that says that almost all predictors are active. We've got a lot of active predictors. Then the convergence rate is root n. That's what I mentioned before. If you have a lot of active predictors, if you're in an abundant regression, you're going to converge at the root n rate. It doesn't matter what p is. If t is a half, so now if we've got 1,000 predictors, and we're thinking, well, maybe something like 30 of them are relevant, then the convergence rate is p to the fourth over root n. So now we don't have to, we lose a little bit. Now the convergence rate is p to the fourth over root n. So we don't have to have nearly the kind of sample sizes you would ordinarily. If t is 0, what does 0 mean? 0 means that the number of predictors is, the number of active predictors is bounded, small, there are 10 or 20, it doesn't matter how big p is, the number of active predictors is bounded. Then you have to have n bigger than p, or root n bigger than root p, which is the convergence rate. And in the interest of time, I think I'm going to skip that, and I'll skip that. Just a little bit on nonlinear regression. There's been a lot of work done on nonlinear regression in chemometrics, trying to figure out replacements for partial least squares. In linear regression in the population, we just think about doing this kind of decomposition. In nonlinear regression, we do this kind of decomposition. So we just stick W transpose X in for X, and then we have the usual model if our model is additive errors. Now, if we're in this condition, then we can just apply an off-the-shelf method. So what I want to do for this is just give you a couple of simple examples, not simple examples, actually they're very complicated examples. This table is from Shan in 2014. He compared a new method, a new nonlinear method for partial least squares, and that's his method number 6. And that method he compared to 5 methods he got from the literature: partial least squares, quadratic partial least squares, kernel partial least squares, locally weighted partial least squares, and partial least squares polynomial, all distinct methods from the chemometrics literature. He invented a new method that's that's kind of like sliced inverse regression, and they call it PLS sliced transform. And if the data set that we're working with has 72 training samples and 43 testing samples, 100 spectral predictors, and it's a multivariate data set, so there are 3 Ys: fat, protein, and water. And these are the root mean square errors for the data sets, or for the methods. And you can see that the PLS transform does better than pretty much all of them. What we did to see how the ideas that we were coming up, to see how they work, is we took the data set and we simply applied partial least squares, the dimension reduction part. So we got W. From W, we got the reduced predictors, and then what did we do? Well, we applied a method, prediction via inverse regression, that one of my former students, Kofi Andragini, proposed in 2009 in a JRSSB paper. Our method, which is basically PLS plus something else, is clearly the best out of all of them. And it didn't require nearly the work or the additional development. So the idea is you can start with PLS, take the weights, and then just take some off-the-shelf method, your favorite off-the-shelf method, for fitting a nonlinear regression. Here's another data set, this one from Caipini and others in 2020. They were interested in using neural networks. And what they did, you can read what it's for there. What they did is they started with 35 samples and P equal to 38,500 spectral predictors. They said, well, we can't handle 38,500 spectral predictors, so they systematically cut it down to 9,340. Then they said, well, we really don't know how to develop a neural network with 9,000 predictors, so we're going to do PCA, and we cut it down to 12. So they started with 38,000 predictors, and then by sort of manipulating the data, they cut it down to 12. The hyperparameters for their neural network, they selected via a Box-Benken design to optimize the desirability function. Their root mean squared prediction error over their testing samples was 8.6 compared to 15.3 for PLS, ordinary PLS. So what we did is we applied what we did before. We took ordinary PLS, we took the W, we took W transpose X, we then applied the previous methodology. We did it to all 38,500 predictors, and we got a root mean squared prediction error of 8.46 compared to the best they could do. And it didn't require nearly the manipulation or the worry about what was happening. Now, this is not an advertisement for prediction via inverse regression. It's an advertisement for partial least squares, saying it's a dimension reduction method, and the reduced predictors can be used in regression in a variety of ways. Now, in closing, I want to mention one thing we're still working on. We're still working on the asymptotic distribution of G transpose times the partial least squares estimator as n and p go to infinity. If you have a really big data set and you want to do inference about parts of beta, how does that work out? Well, it can work out really well. We don't know all the answers yet, but we have kind of hints of answers. This is a little simulation in which the value of p is indicated above the triangles. N is always a half of p. The red histograms are under conditions that we don't expect convergence. Blue histograms are under conditions that we do expect convergence to a standard normal. That's the curve. And if you look down the plots, you see that by the time you get to 2048 predictors with a sample size of 1024, the convergence is really pretty good. The red confirms that we're on the right track. So I think that's it. Whoops. Thank you.
Thank you so much. This is so good, really good. Thank you. We have a couple of maybe just some quick questions since we are a little short in time.
Yeah, I didn't plan on having questions during the talk, so
That's really good.
Sorry, we should have told you that sort of usually our seminars, we ask questions in the middle of the talk as well. We should have checked to see if that would be okay with you.
it was fine to do. I had no problem with that. I would have probably been prepared to have the talk a little bit shorter if I would have known that.
No, it was perfect. It was perfect. Can I ask one more question now that we're at the end of the talk?
Sure, absolutely.
So this idea of using partial least squares with nonlinear regression, which I think is pretty interesting. So previously you could get basically inference for the parameters, for the beta parameters,
Yes.
for the linear regression.
Yes.
What happens in this case with the nonlinear regression?
Well, you can, if you have a nonlinear regression where you know the functional form of the mean, and that functional form of the mean has beta coefficients sitting around in various places, then you can infer about those in the same way that you would infer about them normally. If you don't know what the conditional mean is, and you start by looking at graphs, which can be really helpful, and from the graphs you kind of infer the functional form and then go back and forth, now you're doing a lot of exploratory analysis, and maybe you don't want to try and infer about coefficients from that starting point, but you get a good foundation for your next study.
Yeah, cool. Thank you.
Well, I guess, you know, this is super cool. And I have to say, I'm completely ignorant about this. So I'm glad that you talked to us about this. And now I know, I'm aware. And now I'm curious to go read some more. And, you know, so one thing that's perplexing to me, and so I must be missing something fundamental here, is that I see the benefit if I'm doing prediction. I could see the benefit of that dimension reduction for the sake of prediction performance. If I'm interested in betas in a linear model, and I could say, okay, I can do no dimension reduction, go straight for those betas. But then you can say, but wait, there is a structure here that I can learn, which allows this reduction in dimension. And then but then you have the eta in front, and you have a mapping between the original betas and the W eta vector.
What?
Which I think this is what you were doing at some point. You were finding much better performance by doing this. And I just don't, like, I don't understand why there's such a big gain, because aren't you doing like, I guess the algorithm for getting to a beta estimate is different, but it's still the same statistical problem, which is estimating a beta in a regression. And so without injecting further knowledge, how is it that, and is it just about the Q, knowing the Q in that particular case?
Well, it's about knowing the Q, and it's also about the structure of the data. If Q is 1, think of I have some graphics that would help here, but I'm not going to be able to find them in time. So let me just say it's about the Q, but it's more about the structure that the Q implies. So Q equal to 1 means that the smallest reducing subspace in sigma x that contains beta is one-dimensional. So in effect, that means that beta is parallel to an eigenvector of sigma x, assuming all the eigenvectors of sigma x are unique. If they're not unique, then it's parallel in a dimension reduction subspace setting, but it's the same idea. And so that's the kind of information you're getting. So it's saying that the QWX is irrelevant information. I can throw that away. Now, there's some fuzziness there because you're throwing away things that have been estimated. But all of that comes out in the wash in the likelihood. You're throwing that away and you're left with something that's much smaller and much easier to handle with. The gain comes from throwing that stuff away.
Yeah, because it would be clear to me if I knew Q that, okay, now it's actually strong structure that I'm putting in. And so I can see the clear gains. And now you say, okay, in practice, I don't know Q. I have to estimate it, but
Yep.
that actually does not contribute. Is that a part of the story that it ends up being not?
Well, it does contribute, but it contributes it kind of muddies the water a little bit, but it doesn't contribute to such a degree that you say, oh, why am I bothering with this? Now, the best method the method that I think is the best was developed by a former student of mine, Dan Eck, who is now at Champaign-Urbana. And what he did is he said, I'm going to do model averaging. I'm going to take Q equal to 1 and I'm going to get the BIC value. I'm going to take Q equal to 2 and get BIC. And then I'm going to use a function of those BIC values to do a weighted combination of all the beta hats. That's my new beta hat. And you can get the standard error of that. And usually what happens is that there's a little additional fuzz, but if your inference about Q, if the information is strong, you're in good shape. So if you think about BIC values, if you think you've got one huge BIC value, this is it. This is or small, depending on how you're doing it. This is the one. Then it's not going to matter. But if you have if you've got a dozen BIC values that are all about the same, they're different, but they're all about the same, then the information is going to be spread over that range, and you're going to incur additional error. Now, how important is that range? Well, if you've got 100 predictors, so Q could range from 0 up to 100, and your interval only covers 10, then that's really still a reduction, and you still get a substantial gain, although it will not be as much as you would imagine given Q equals 1 or 2 or 3 or whatever it is.
Oh, super useful. Thank you. Thanks so much.
A lot of this stuff is spelled out in the book, if you wanted to get that.
Yeah, this is a great endorsement for the book. Great publicity. I mean, I do want to go get it and look at the details now. So thank you.
Then let me add one thing. I usually recommend that people buy 3 copies. One for home, one for the office, and one for your car in case you get stuck in traffic.
And one for my mom too.
Okay, there you go, 4. I missed one.
This is great. Fantastic. Thank you so much, Dennis.
Yeah, thank you very much, Dennis. It was really interesting.
If people, if you know, 1 or 2 of you continue working with this and have questions, feel free to drop me an email.
Yes.
Thank you.
Well, dude,
Thank
you.
you.
Thank you very much. Thank you very, very much.
Evening. Bye.
Bye.
Bye-bye.
Bye.
Bye-bye.